Hi, students. This is a continuation, the final part of the Chapter 22 lecture. Again, Chapter 22 is on electromagnetic induction. See, continued. And this would be part 3. All right, so tonight, what we have left is a couple of topics, and that'll complete the topic of the subject electromagnetic induction. All right. So first topic I want to talk about goes right into our development of the third of the 3 circuit elements. So as I said in this class, we're gonna cover 3 major circuit elements, that basically things that we put on a circuit, devices that we put on a circuit. We're gonna cover those elements in this class, and one of them is a resistor, one is the capacitor, and one is what we call the inductor. All right. So tonight we're gonna start off by talking about what's called inductance. All right, so that's our topic. So before we talk about inductance, so let's kind of recall the concept of capacitance. So remember back in chapter 18, we discussed the concept of capacitance, and the idea was that basically a capacitor was an arrangement, to recall. I'm going to develop the concept of inductance by comparing with capacitance. So recall that a capacitor is an arrangement such that if you place a charge Q on its plates, capital Q, a potential difference V appears across the plates, such that Q equals C times V, right? Where C is called the capacitance. All right, and so we are literally, the purpose of a capacitor, again, we looked at the parallel plate arrangement. It could be any 2 conductors that are in close proximity to one another. We choose something like a parallel plate because we can actually solve that equation. But the thing is, we could do any other highly symmetrical arrangement. For instance, we could use 2 concentric cylinders. A cylinder along a main axis, and then another cylinder that's has either an empty airspace in between or a dielectric, or we can have a sphere inside of another sphere. But we pick, again, the geometry to solve the formula for the capacitance in those other cases requires integral calculus. We can actually solve for the parallel plate capacitance as I did in class, or as I did in the lecture, by not using integral calculus. I mean, the math is easy enough where integral calculus is not really necessary. And we see that the capacitance actually only depends on the geometry. All right, and so capacitors are related with capacitors contain or have a property called capacitance, and the units of capacitance is the farad. So the unit of capacitance again, what is it again? So again, as I said, Q equals CV. So essentially what I can say is, well, C is Q over V, or Coulomb per volt. And if I get an arrangement like that, I call that the farad. Typically, I use a capital F, right? So basically, 1 Coulomb per volt equals 1 farad. And we named that after Michael Faraday, of course. Now, so that's the point, is we're basically storing charge on the plates of the capacitor. Okay. Now, we have a magnetic equivalent. So again, capacitor deals with charge, and of course, electricity generally is one usually generally talks about charge. Talk about a charge distribution. Well, we're talking about magnetism. We talk about current. And so we have what's called an inductor now. So an inductor. Okay, so now we're going to go one step further and talk about the magnetic correspondence. An inductor is an arrangement such that if you establish a current I, so current I in the windings a magnetic flux cap phi links each winding. Let me draw a picture in a moment. The inductance L is defined by and we say L is N phi over I. Okay, so back in chapter 18, we had the capacitor. Just kind of draw, an analogy here. So what do we do with the capacitor? Well, we had two parallel plates. And this is all review. We know that there is a charge positive Q in the top plate, negative cap Q in the bottom plate. And essentially, we can imagine there being hooked up to a battery. All right, and so I'm running out of space here. Let's see. Draw this over here. All right, so we had back in chapter 18, we had two parallel plates. Two parallel conducting plates. That's how I made a capacitor. I had a positive cap Q charge in the top plate and a negative cap Q charge in the bottom plate. And of course, what did I do? I connected the plates together to form a battery, or connected to a battery. Okay, so we have a battery V. And of course, when you have a potential difference, you essentially will separate the charge. When you have separated charge, you always have a electric field. Electric field will go, if you imagine all the charges, all the positive charges, excess positive charges, because it's a conductor, it's going to be on the surface of the conductor. So, and an equal amount of negative charges will be on the surface of the other conducting plate. And so electric fields will go as follows. Every single charge electric field line will start from a charge and go to a negative charge, start from a positive charge among all the excess positive charges on the surface of the top plate, and go to a corresponding negative charge. And of course, as we remember, the electric field must leave and enter a conductor perpendicularly. It must do so in a normal direction to be more mathematically precise. So this is the electric field. All right, so this is what's going on, what we talked about in chapter 18 with the capacitor. Well, the inductor, as I have said, we have the go-to for electricity is the parallel plate. So the go-to for magnetism is going to be the coil. So I'll do a cutaway of the coil. So imagine here on the magnetic equivalent, the top, I have current coming in to the top. I'll kind of have square coils for easy drawing purposes. And on the bottom, I have current coming out. Yeah, this is a cutaway. This really represents a coil. Wire, so essentially, current is going in a loop. So current is coming through for each one of these windings. Current comes through the top. If you watch my right hand, the right hand rule, my fingers are going to curl around, and current's going to come out the bottom. So literally, this is a cutaway. It's just showing you that there is current going in and out of each winding of this basically a solenoid. And of course, by the right hand rule, which way would the current be going? Well, it's going. I'm sorry, I'm doing this backwards. It's going into the bottom. That's the tail feathers coming out the top. So again, it's going into the bottom and coming out the top. I said the exact opposite of what I thought. And so, of course, by the right hand rule, by Faraday's law, which direction is the magnetic field going to go? Well, again, I use my right hand. I curl my fingers along with the coil, along with the wire or the current. So it's going to go into the bottom and out the top, into the bottom, out the top. And so the magnetic field is going to be going to the right. So I have nice uniform magnetic field, strong uniform magnetic field, parallel to the axis of this solenoid. Again, it's supposed to be uniform. And so again, the idea with the inductor, now this is a capacitor. What I'm seeing right here, this parallel plate, that's a capacitor. And what I'm showing you on the side here is an inductor. Again, to not confuse, it's a cutaway. Tail feathers always mean going into the board. The head of the arrow is coming out at you. That's those dots mean coming out of the board. So if you follow my fingers, I'm going into the board and a winding down at the bottom of this coil, and it's going around and it's coming out the top of the coil. And of course, by the right hand rule, by Ampere's law, a nice strong uniform magnetic field is going through the axis of this coil. Okay, so again, I have the ability to make a nice uniform electric field with a parallel plate arrangement. I have the ability to make a nice uniform magnetic field with the coil. So the go-to arrangement for electricity was the parallel conducting plates. The go-to arrangement for magnetism is the coil. All right, and in so doing, this is such a go-to arrangement that I made a circuit element out of it. I call this a parallel plate capacitor. And this coil is such a go-to arrangement that that we can make a circuit element out of it too. And that's our third circuit element. That's the inductor. So at this point, we now have the resistor, the capacitor, and the inductor. Now, as I said earlier, N times phi is called a flux linkage, number of flux linkages. So each one of these turns of wire is going to contribute magnetic flux. Remember, there is an area, it's a cross-sectional area in the solenoid. All right, so really what really matters is the dot product, or the dot product B dot A, or in this case is B and the area, cross-sectional area, normal, the cross-sectional area are aligned with each other. B dot A becomes B times A. So what really matters is the magnetic flux. So every single one of these windings, every one of them contributes an amount of flux. Well, we have N times phi of those. So phi is considered what's called a flux linkage. And N times phi is the number of magnetic flux linkages. So N times phi is officially called the number of flux linkages. You divide that by the current I. And that is the definition of what we call inductance. And so again, that's let's take a look at what the units of inductance would be. We have a brand new unit here. So again, let's remind ourselves that N times phi, look at the vocabulary now. N times phi is considered a number of flux linkages, all right? So cap N, that's the number of windings in the coil. Cap phi is going to be the magnetic flux per winding, and this is called the number of flux linkages. That's the official physics term. Okay, now I have again L is N cap phi over I. We got to assign units to this, all right? So of course N is unitless. So what do we have? Cap phi. What do we say cap phi was again? That's B times A. It's a magnetic flux, right? Remember cap phi? Officially, cap phi is, well, in a more simple way, it's the dot product of B times A. But in this particular case, it's just B times A because the area normal, the cross-sectional area, and the magnetic field are aligned. They're both along the axis of the coil. So what is that? That's Tesla meters squared. Okay, so on top I have Tesla meters squared, and on the bottom, well, what's the unit for current? Well, it's the ampere. So the inductance officially is a Tesla meter squared per ampere. When I see that combination of units, we honor another physicist. We refer to 1 Henry. We abbreviate that as 1 capital H, and that's 1 Tesla meter squared per ampere. Now, so who is Henry? Well, so basically, Joseph Henry is, or was, an American physicist. We have another American now. I think this is our third one. We had Benjamin Franklin first, Edwin Hall, and now we have Joseph Henry. So we're starting to see Americans pop up in the physics world now. So Joseph Henry is an American physicist who co-discovered the law of induction. Along with Michael Faraday. Michael Faraday is much more famous, but But I'm here to co-discover of one of the most important laws of all of science, basically a law that gives you technology, like this law does, then yeah, I think you're important enough to at least have a unit named after you. So we have 1 Henry. So inductance is in henries. Okay. So you have magnetic flux is in Webers, inductance is in henries. All right. So now let's calculate the inductance of something that we know about. So we talked about earlier on. We talked about what's called a solenoid. So let's figure out the inductance of a solenoid. So again, we have this term inductance. What does it mean? Well, let's kind of get some physical feel about what inductance means. Let's calculate the inductance of a solenoid. So inductance of a solenoid. So to remind ourselves, a solenoid is basically a tight coil. So again, a solenoid is a tight coil. Usually, we are given the cross-sectional area of the solenoid. Maybe the radius or diameter. And the number of turns or windings as people call it, windings per unit length. And that's usually given by little n. The number of windings, the total number of windings, oftentimes is given by capital N, right? But little n, you pull a solenoid off the shelf, they'll usually tell you what little n is. It's either on the label or on the box or whatever it is. Usually that comes with the solenoid. Somebody will tell you what little n is. Okay, so that's usually the number you're given. All right, so let's first of all figure out what the inductance is. All right, so and remember, why do we have a solenoid? A solenoid has a current I going through its windings. A strong uniform magnetic field B within parallel to the axis, or I guess the central axis, and no magnetic field outside the solenoid. Just outside the solenoid, nothing. Because the windings are very, very tight and there's a very high symmetry. So it's great for generating strong uniform magnetic fields. Oftentimes you'll have, your car has solenoids in it. Many, a lot of machinery that deals with, operation with magnetism, like motors, will have solenoids in it. All right, so that's what a solenoid is. Very important for our technology. So let's apply it. Let's try to figure out what the inductance is for a solenoid. So let's start off with the definition of inductance. First and foremost, what did I say it was? I said that L, the inductance, is cap N B over I. That's your inductance. All right. So now, cap N, remember, I usually, that again, cap N is the total number of windings. Now, sometimes you're given the length of the solenoid, or you can just measure length of the solenoid. So let L, call it little l, be the length of the solenoid. So then what? Well, then little n would be what? It'd be cap N over L. So instead of writing big capital N up there, what I can actually do instead is solve for it. Cap N is going to be little n, little l. All right. So I can, instead of writing cap N, I mean, that is the official language of what an inductance is in general. You use the total number of flux linkages. But for a solenoid, we usually are not given capital N. We are usually, I'm usually given how many windings there are per unit length, and I can go and get some sort of a measuring device and measure the length of the solenoid. So I can very easily replace this. And so instead of writing this, I can instead write cap N as just little n, little l times cap phi divided by I. All right, so I can instead write that. All right, now I've taken care of cap N. What about phi? Well, what is phi again? Again, generally speaking, it's the magnetic flux. Usually, it would be the dot product of the magnetic field and the area. Again, the direction area is a vector in physics, and so the direction of the area is given by the area normal. Well, you know, B in a solenoid is uniform and along the cylindrical axis. Nice uniform magnetic field. A, the area normal, of the cross-sectional area of the solenoid is also along or also pointed in the direction of the cylindrical axis. I'm barely kidding. All right. All right, so that means, since they're aligned, that means that B dot A is really B times A. Or B times A times cosine of 0, or just BA. All right, and so with that said, I can write phi now. L is going to be now NL, and then I'm going to have BA divided by I. Right. That's what I have so far. And if you go back to our study of chapter 21, that's where we talked about the solenoid. In chapter 21, we gave a form, or we derived a formula for the magnetic field of the solenoid. And if you recall, we derived that to be B is mu naught N I. All right, and so I could then simplify even further and say, okay, well, if I know that B is mu naught N I, well, that's the magnetic field in a solenoid. So I can then say, well, okay, then L is going to be NL. Now I have mu naught N I A divided by I. And nicely, these I's cancel out. And what I now have is that L, magnetic flux, so gather everything together, I'll have, generally speaking, I write it like this. Cap L over little l. Okay, so I break the L down. Let's see, I have a mu naught, I have an N squared, and I have an A. A mu naught N squared A. I usually write the inductance per unit length. For a solenoid. Now, why do I want to write it like this? Why do I maybe not want to put the L on the right-hand side? Well, the reason being is, you can have, when you get, you have nice parallel magnetic field lines through the center of the solenoid. But when you get near the mouth of the solenoid, sometimes they diverge. All right, and so if I assume, or if we assume that a solenoid, or we assume a solenoid whose length is much greater than its area, basically a long solenoid, then we can neglect the tendency, or neglect the tendency this way of magnetic field lines to slightly diverge from parallel at the mouth of the solenoid, or that at the ends of the solenoid. Okay, so this is basically an equivalent statement. This is the equivalent statement that you would use for capacitors. So this statement for an inductor, or for a solenoid, or I want to say for an inductor. Is equivalent to the assumption of large plate area. For capacitors. So as to neglect fringing of the electric field at the ends. Or at the edges. All right. So again, for a capacitor, for parallel plate arrangement, we want to make the assumption that there is definitely a parallel uniform electric field going from the positive plate to the negative plate. Okay. Now we know that if we don't make the assumption of a relatively large area compared to the spacing, then we have to worry about fringing effects of the electric field at the ends. If we let the area be large compared to the spacing of the capacitor, then we can neglect the fringing effects of the electric field toward the ends or toward the edges. This is the same statement. If we allow the inductor or the solenoid to be long enough compared to its area, we can again neglect the tendency for the magnetic field to diverge from its nice uniform parallel condition that it has throughout almost the entirety of the inside of the solenoid. And so we can neglect that effect of that slight diverging effect. And that's what this is saying. If I can make this statement, then I can multiply that little L up to the right-hand side. So if this statement is good, then essentially if that's the case, then I can write, instead I can actually then write that L is equal to mu naught L N squared A. This is for solenoid whose length is much greater than its area. Okay, so again, this is the inductance for a solenoid, and in fact, you can use a solenoid as an inductor. In fact, I mean as we remember our circuit elements, we use the parallel plate symbol for the capacitor, right? We use this little zigzag for the resistor, and in fact, for the inductor, we actually use in our circuitry, we use a little coil. And we put, so again, the actual circuit element, the symbol for that circuit element is a little coil. And that's what we put on a circuit when we want to consider an inductor. Now, so now we want to, now that we've defined the inductance, we actually like to now lead to actually putting it onto a circuit. All right, so let's imagine putting it as part of a circuit now. So let's, I'm going to kind of blow up a picture of an inductor on a circuit, and let's take a look at some interesting phenomena. All right, so I'm going to draw a little circuit. Not going to be very pretty. Yeah. Okay, this is a variable resistor. Typically, we'll make it long. Okay. Okay, so now we're going to connect with an inductor. Now I'm going to really blow this thing up to make it look kind of big. So it's going to be it's got a coil, basically. Okay, so I have a coil. Come around, I'm going to have a battery on the end. And I'm going to connect the coil someplace on the resistor. Remember, the resistor, depending upon how long the resistor is, remember, resistor has resistivity, and rho L over A. I can control the resistance by how much length I allow the resistor to have. So again, you have a variable resistor like a rheostat. Where you actually touch along the resistor, you're determining the resistance. Again, you're determining the area. All right, so this is a variable resistor. This is an inductor. And it's very, very exaggerated, very blown up. Here's my battery. Call it epsilon. And I have a resistor on it. Okay, so now what's going to happen? I turn on this. I turn on this. I throw a switch. I didn't really put a little switch on here. I throw a little switch S. What happens is, well, again, this is the positive side of the battery. So a current is going to be generated in this coil. So again, there will be a current that'll as soon as I close the loop, because of the battery, we will now have a current established in the loop. Okay, so what's the current going to do? Well, the current is now going to go through these windings. Okay, so again, the current's going to go through here, and maybe like, here's an example of part of the current right there. And it's going to go through these windings, and it's going to come back down, and it'll finish the circuit. So what happens when you have a current going through a set of windings? Well, again, you want to employ Ampere's law. Ampere's law says, okay, well, I have a current that's essentially going through this set of windings. Well, I'm going to realize that there's going to now be a magnetic flux. So actually, it's coming around like this. Yeah. So we're going to actually have a magnetic flux that's going to be established. All right. And so what's happening here is that, well, you get this magnetic flux, you get this change. And well, the reality is, actually, let me draw this a little bit differently. Draw this current. All right, so I have my current going up. All right, so the current's going to go up, and I'm establishing a magnetic flux to the right. So I have a magnetic field that's going to be established in the right through this loop. Okay, so again, I have a solenoid that I've attached. I have a coil that I've attached. Because current is going through this coil, a magnetic field is generated through this coil because of Ampere's law. So again, this magnetic field exists because of Ampere's law. Okay, again, just like the discussion of the transformer. Again, I have a current going through a coil. There's going to be a magnetic flux. All right. Now, here's something that's very interesting. Let's say that that this particular current, because of this. So let's say that the current starts from 0 and this gradually builds up. All right, we're going to find out that the inductor actually causes the current to slow down. So again, as opposed to initially, if there's no actual inductor there, the current goes straight to epsilon over R. But the inductor kind of slows it down, and we're going to find out that what's actually happening is that, well, initially there's no magnetic flux in this coil. But now the magnetic flux, because it's being built up, the magnetic flux is changing. Okay, this now invokes Lenz's law. Lenz's law says, oh, no, I don't like change. I'm going to oppose that. I'm going to oppose that change. I'm going to oppose it with an EMF. Basically, I'm going to oppose it with an EMF basically caused that I'm inducing. So Lenz's law will induce an EMF. Essentially, this actually causes the voltage drop. So you can think of there's always a voltage drop for any circuit element. We had IR for Ohm's law for a resistor. We had Q over C for the capacitor. We need to establish, a voltage drop, and that's because of Lenz's law. All right, and so we see what's called a self-induction. All right, and so an induced EMF. Let me change pens here. So an induced EMF appears in the coil. And if we change the current in that same coil, now I didn't point something out to you, but when I drew this epsilon, I put a little open circle at the end. This means it's time varying. This is actually a time varying epsilon. So it's actually going to cause a change. It's going to constantly vary the current in time. So given that you have an EMF, the EMF of the battery is going to vary in time. That's going to vary the current in time. So you're going to get a time rated, basically the magnetic flux in the coil will vary in time. And so just like with the transformer, you're going to have an induced EMF caused by Lenz's law. Okay, and so so again, this induced EMF is going to the induced EMF will, I guess I'll call this epsilon sub L. The induced EMF will oppose. So the induced EMF is due to Faraday's law, with Lenz's law, and it opposes the changing or the time varying magnetic flux in the coil. Caused by the time varying current. Which is caused by the time varying EMF. Call it epsilon for short. Okay, so this varies in time, and so that causes the current to vary, and that causes the magnetic flux to vary in time because of Ampere's law, and of course, because of this changing magnetic flux, this magnetic flux comes about. This changing this EMF caused by this changing magnetic flux is caused by Faraday's law with Lenz's law. And so we see there's an opposing EMF. And we call this a self-induced EMF. We call this self-induction. So this EMF is called the self-induced EMF. EMF that's induced just to oppose the change in the magnetic flux. That's because of Lenz's law. So the EMF in the coil is called a self-induced EMF. Okay. Very important term. And this is called, this phenomena is called self-induction. Self-induction. That is why we put an inductor on a circuit. Self-induction. Okay, so let's look at how we can actually express the self-induction. We can actually express this self-induction in terms of the inductance. So how do we do that? Well, we start off by looking at the number of flux linkages again, and phi. So remember what the definition of inductance is. Inductance is cap N times cap phi divided by I. That is the inductance. All right, that again is the number of flux linkages on top. Cap N is the number of windings in the coil, and I is the current going through the coil. Now let's simple algebra tells us that I can substitute for the flux linkage, and N cap N phi equals Li. And of course, I know that Faraday's law is expressed as a time-varying magnetic flux. So Faraday's law is what? This self-induced EMF is caused by Faraday's law. All right, so this EMF, we'll call it epsilon sub L, is due to Faraday's law. So it's going to be negative cap, so negative delta of cap N phi with respect to T. I mean, that is Faraday's law. The self-induced EMF obeys Faraday's law. So again, the self-induced EMF epsilon sub L obeys Faraday's law. Hence, I can write this relationship. That is Faraday's law. All right. So, well, look at this. I have cap N phi in the parentheses here in the time rate of change operation. Well, I can substitute that directly for Li. All right. And so again, from this relationship, for the basically the definition of the inductance, I'm substituting for the number of flux linkages. So epsilon sub L now becomes negative delta of Li with respect to T. L is a property of the inductor. That's a constant. That doesn't change. The only thing that's going to change is the current. The current is time varying. So L is a constant. It pulls out. All right. And so L, the inductance. So the inductance L is a property of the inductor. So it is a constant. It does not get affected by the time rate of change operator. I can pull it out. So then epsilon sub L becomes negative L delta I with respect to T. That is the self-induced EMF. Now, of course, if I really want to do the job right, I'd want an instantaneous self-induced EMF. What does that require? That requires integral calculus, or sorry, differential calculus. So to get the instantaneous induced EMF requires differential calculus. And so I would substitute my deltas for D's. And I would then say that the EMF sub L is negative L di dt. Let me write this up. I'm running out of space here. So in reality, I would write, if I want instantaneous, I would say that epsilon sub L is negative L di dt. This is the first derivative of the current with respect to time. And this is the instantaneous EMF. Self-induced EMF, right? This is the one we're going to use in this class. So the self-induced EMF that is experienced by the circuit because of in this because it has this inductor as part of the circuit, it will be negative. So again, it's a drop times the inductance times the time rate of change of the current of the current. So again, what changes in time is the current. Okay, so that is the self-induced EMF. Okay. And again, the direction of the self-induced EMF is determined by Lenz's law. So again, the self-induced EMF is negative L delta I with respect to t. All right. So in any inductor, including a solenoid, or such as a coil or a solenoid, okay, a self-induced EMF appears. Whenever the current changes with time. All right, so you have a time varying current, you will have a self-induced EMF caused by what? Caused by Faraday's law. All right. You can find the direction. You can find the direction of the self-induced EMF. And you'd use Lenz's law. Lenz's law always wants to oppose change. Now the minus sign above the minus sign of this equation, all right, so that minus sign represents the fact that the law states the self-EMF will oppose the change that brings it about. Okay, so again, any inductors is a coil or a solenoid. A self-induced EMF appears whenever the current changes with time. Again, I drew a little circle at the end, at the bottom of the arrow that represents the EMF, because that circle is just nomenclature that says it's time varying. And then you can find the direction by, and then self-induced EMF using Lenz's law. The fact you have a minus sign here states that the self-induced EMF will oppose the change that brings it about. Again, it's because of Lenz's law. Lenz's law is the law of opposition. It wants to oppose any change. Okay, now let's kind of go back to somewhat like the drawing that we very first started, our very first drawing that we had when we started this lecture. I'm going to draw a little differently though. And I'm going to match up a couple of different wire loops together with each other. Okay, so let's let me draw a little picture here. I'm going to talk about another concept. All right, so I need a little real estate to talk about this. So let's draw. All right. Okay, let's see here. All right, there's one loop. I'll have another loop here. All right. All right, two loops. I'll call it coil 1 and coil 2. All right. In my first picture, coil 1 has a battery, and coil 2 does not. Coil 2 instead has a galvanometer. All right. Now, this is coil 1. It's going to have N1 turns of wire. Coil 2 will have N2 turns of wire. Now, what I want to do is I want to actually turn on a current that's going to be time varying. So I'll turn on this current here, and I'll have a current I1 coming up, and I1 coming back down. All right, and there's going to be, even if I1 was steady, again, what am I going to have? I'm going to have, if I do this right, I'll have, yeah, I'll have the current coming around. So the current's going to be going up and around this way if I do this right. And so I'm going to have current. No, that's not the way I want to draw it. Give me a moment. Let's see. All right, something like that. So the idea is I want the current to actually be going over, such that, if you follow my fingers on my left-hand loop, I want the magnetic field to be going through the left. All right, so I want magnetic field lines to be going through. Call this B1. Okay. So what we have here is, I'm going to imagine that the wire, the current I1 varies in time. And I'm going to imagine that the second loop is lined up, they're basically lined up, their axes coincide. They have the same axes. The axis that goes through each of the center of the loops, even though one looks bigger than the other, the axes they're lined up just right. All right, so now the so if I were to just imagine a steady current going through this coil right now. All right, so I1 going about or flowing about the coil of wire of loop of coil flowing about coil 1 will generate magnetic field B1, which will go through the way magnetic field lines go. I mean, eventually it's going to come around and come through the right loop. I didn't draw the whole picture. We'll go through loop 2 or coil 2. All right. So again, now so again, I would establish the following. Again, I don't even care about the current being time varying at this point. What I actually have now is I have a current generating a magnetic flux through B1, just employing Ampere's law. So now this is going to cause a magnetic flux and the secondary in coil number 2 as well. Now, if the current is not time varying, there's not going to be a deflection of the galvanometer in coil 2, but there will be a flux. And so we can define what is called a mutual inductance. So we define a mutual inductance. So essentially, the magnetic field B1 also flows through coil 2, which has the same central axis as coil 1. And is nearby. All right, and so in that particular case, well, we have now a magnetic field that's going, a magnetic flux that's going through coil number 2 because of the current that's generated. So the current in coil number 1, we call that I1, generated a magnetic flux. Or sorry, generated magnetic flux, and in particular a magnetic field. There's a magnetic flux that's happening in coil 1, but in particular there's a magnetic field that's going to go through coil 1, the B1, and B1 is also going to go through coil. It's also going to go through coil 2. All right, and so actually I think I have this backwards. Give me a moment. I meant to draw this, but I meant to draw this the original way. Sorry about this. Give me a moment. I had the magnetic field lines going the wrong way, so I really want my magnetic field to go this way. So I really want coil to look like this. I want my magnetic field to come down. That way, my magnetic, so now my current to go down, the way my magnetic field is going to be going to the right. All right, there's my magnetic field. All right, so B1 is generated from coil 1 and it's going through coil 2. All right, so all right, so again, I have a current I1 caused by the battery in coil 1. That current is going to cause a magnetic field B1, and that magnetic field is also going to go through coil 2. All right, so again, coil 2 experiences a magnetic flux. We can define what's called a mutual inductance. We define a mutual inductance call it M21, which is going to be given as number of flux linkages N2 B sub 2(1) divided by I1. And again, M21, so basically P21 is the flux through coil 2 due to coil 1. And so that's where this 2,1 comes from. This M21 is called the mutual inductance. All right, so it has the same units as inductance. I mean, it's also going to have the units of Henrys. You have a unit of Henry. And so again, it's built the same way. It's number of flux linkages divided by the current. Now let's look at this very carefully. The flux linkages is the flux linkages due to coil 2. That's N2. That's the number of coils, number of turns in wire 2. P21 is the flux into due to what's going the magnetic field from 1. Okay, so again, there's going to be a magnetic field coming through. Now the magnetic field is going to have a certain flux on the left because maybe the coils have a larger area, and on the right maybe the coils are smaller. You're still going to have the magnetic fields coming along, but you would have a different flux, and that would be the flux due to the magnetic field B1 going through. So you have basically a flux through loop 2 due to loop 1. And what current are we talking about? Well, it's going to be the current I1. I1 is what's driving this. So we have the mutual inductance. So let's back this up and review one more time here. I have two coils side by side. One coil that has a battery, coil 1 has a battery epsilon, we'll say. And I have another coil that does not have a battery. This is a galvanometer. Okay, that's going to measure if there's any kind of current in the second loop. Now, because there is a circuit here, because the battery is connected, a current I1 will essentially go through this loop. It'll go through the coil. It's going to go through the coil, and by Ampere's law, it'll generate a magnetic field through coil 1. And hence, it'll give you a magnetic flux through coil 1. But those magnetic field lines are also going to go through coil 2. And so coil 2 is going to also have a flux set up. It'll have a flux B21, the flux in coil 2 due to the magnetic field from coil 1. And the number of flux linkages, well, what would you use? Well, you'd use the number of turns in this coil. That's the one you're talking about, coil 2. And what current is setting this up? It's I1. I1 is the current that's causing all of this to happen. That's the current that's in the battery that's causing this to happen. Okay, now let's go one step further. We can then say, okay, well, fine, we have this nice formula for the mutual inductance. Okay, that's what's causing everything to happen. So let me erase a lot of this and rewrite the mutual inductance formula. So what did I say? I said that we have this mutual inductance. M is basically N2 due to 1. So we're talking about coil 2 now because of coil 1, due to what's going on in coil 1. Again, the number of flux linkages is we're talking about coil 2, so we're going to use the number of windings in coil 2. Again, this is flux in coil 2 due to the magnetic field from or the current in magnetic field from coil 1. And we're going to divide the current of interest, the current that's causing all of this to happen, is set up in coil 1. So that's I1. Again, mutual inductance. Well, we're gonna essentially cross multiply. We're gonna set things up like I did before. We're gonna say, well, we have M21 I1 equals N2 B21. And then what do we want to do? We're going to take the time rate of change on both sides. Well, M21 is a property of this arrangement, the mutual inductance. And N2, again, is a constant. That's the number of coils in wire 2. So they're not going to participate in time rate of change. The only variables that will participate in time rate of change are I and phi. So applying a time rate of change operation, I get M21 delta I1 with respect to t. If I1 varies in time, and that's going to be given as N2 times delta B21 with respect to t. Again, we're now allowing I1 to vary with time. All right. In that case, you'd have a time varying flux 2-1 B21 in coil 2. All right. And so again, we would define the right hand side looks like it's basically Faraday's law. So we'd say that the EMF set up in coil 2 right here will be negative M21 delta I1 with respect to t. Again, this is this EMF. This is the EMF induced. This is the EMF from Faraday's law in coil 2. Again, Faraday's law, you see this form in the right-hand side. So again, I can call the entire right-hand side as epsilon 2. I can flip about my equal sign, and then this is all I have now. Again, this is the negative from Faraday's law. Negative M2N delta I1 respect to T. So again, this is Faraday's law, except for the negative sign that comes along with it because of Lenz's law. So again, I put that negative sign here. All right, so again, Faraday's law coming into play. If you take the time rate of change of this flux linkage of this equation with the flux linkages, well, again, this is what you're going to get. And right here, the right-hand side is Faraday's law with respect to a time-varying magnetic flux in loop 2, except for the minus sign. So that minus sign then gets written right here. So again, the EMF induced in coil 2 is equal to negative M21. That's the mutual inductance times the time rate of change of I1 with respect to T. That's a coil from wire 1. Okay, so I can switch roles at this point. So again, let me parking lot this equation. So let me now switch roles and let coil 2 do the work. Let's remind ourselves what this last equation was. It's and put in the parking lot that epsilon 2 is negative M21 delta I1 with respect to T. Okay, putting that in the parking lot. All right, now let's switch roles. Let's now have coil 2 possess the battery and coil 1 possess the ammeter. All right, so let's change this around a little bit. We're going to switch roles. This one gets the ammeter now, and this one gets the battery. Or it's not the ammeter, with the galvanometer. We'll say. This one now has the battery. All right, so the way this is set up, let me redraw my picture here a little bit. Let's just redraw the whole thing. Trying to conserve something that's not going to be conserved. So let's see here. Draw coil 2 first. All right, I want the magnetic field going this way, so I want to have that. And then at least that's going to be an epsilon. On the other side, I want to do it before. I want these to be lined up. So let's see. All right. So now we have coil 2 and coil 1. Coil 2 now has a battery. Coil 1 just has a galvanometer. All right, and of course, we now will have a current I2 in coil 2. I2 will come around such that I have magnetic field going through here. And we would call this B2. And of course, it would be the same kind of situation. I could do the exact same math and say, well, I have a magnetic flux that's caught, that's in coil 2. I have a field B2. That field is going to go through coil 1. And coil 1 is going to experience what? It's going to experience a flux basically in 1 due to 2. All right, and so in that particular case, what would we say? Well, we would say that we would have, I would define an M12, all right? And I would say that that's going to equal N1 B12 over what? I2. Again, exact same math as I did before. What would I do then? I would then cross multiply. Again, this is a new mutual inductance. This is not M21. This is M12. This is an inductance that's basically in coil 1 due to the current in the magnetic field B2 coming from coil 2. So again, the number of flux linkages I care about now is in coil 1. That's the coil that's now receiving the magnetic field that was generated from coil 2. And again, B12 says that's the magnetic flux in 1 due to 2. And what current that is driving all this? Well, that's the current I2 in coil 2. Again, very deja vu. We just got done talking about when we did it the other way around. Let's cross multiply and we say, okay, well, again, the same mathematics applies. M12 I2 is N1 B sub 1 2. I take the time rate of change of both sides. I get M12 delta I2 with respect to T is N1 delta B 1 2 with respect to T. Again, N1 is the number of turns of wire in coil 1, and M12 again is my mutual inductance. Again, considering coil 1 reacting to coil 2, what's coming from coil 2. All right, and so by the same token, look at this. This is Faraday's law of induction again. This says, well, I'm really focusing now on wire 1, on coil 1. I have N1 turns, and there is this time rate of change of this mutual or this magnetic flux that's in coil 1. Well, that's going to be Faraday's law of induction, except except for that negative sign. So I would again write that epsilon 1, the EMF that's set up in coil 1, would be negative M12 delta I2 with respect to T. Again, the EMF set up in coil 1 is negative M12 times the time rate of change of the current in coil 2 with respect to T. Just like when I had the EMF set up in coil 2, that's negative M21 times the time rate of change of the current I1 in coil 1. All right, so again, I have two of these equations. I can write them side by side. Mathematics is absolutely the same. And so now, this is not in any way obvious, but I state without proof that at this point, that M12 equals M21, and we can just say it's equal to M. The two mutual inductances are equal to each other. So we actually call M's. Again, this is not obvious. This is true. And I state this without proof. I don't really state many things in class without proof, but this is beyond the level of this class for sure. And so I would say then that what I can actually now write is that this is going to be, these are now M. So delta I1 with respect to T, delta I2 with respect to T. All right, so those are the two equations from the considering mutual inductance relationship or phenomena. All right, and so again, M is the mutual inductance. It has the same units as L. So M is the mutual inductance. It has the same units as regular inductance. Which are Henrys. Or the Henry. Or which is the Henry, we'll say. Okay. Now, that is the concept of mutual inductance. Now, I'm going to do a few problems here. Don't worry. I want to talk about one more little state property before we start working a few problems. Okay, and so now, like we said with the capacitor, a capacitor stores energy. So does an inductor. So capacitor stores electrical energy, an inductor stores magnetic energy. All right. So we talk about so again, we know from Lenz's law that inductances oppose changes in currents. And it's kind of like understand what we're talking about here now. Again, this opposition to a change in current is really due to Lenz's law again. Lenz's law opposes change. Okay. There's an alternative way there's an alternative way of to look at opposition in terms of energy. To look at this opposition in terms of energy. Okay, and so energy is stored in a magnetic field. Okay, and so essentially, it takes time. It takes time to build up this energy. So it takes time to build up this energy, and it takes time to deplete energy as well. Okay, so it takes time to build up the energy. It also takes time to deplete it. And so, hence, there is opposition to rapid change. When you take, when you put an inductor in a system, because of this effect of opposition, it's going to cause a slowing down of the current. We're going to see this a little bit when we talk about our last topic, which is our RL circuits. We're going to see how that the current doesn't just go to a maximum value very quickly. It gradually increases in asymptote, and gradually increases in time. All right, so moving on, taking all this into account, in an inductor, just kind of think about what's going on in an inductor. The magnetic field is directly proportional to the current. True. We saw that with the solenoid, remember? Remember the solenoid? Magnetic field is mu naught Ni. So again, the magnetic field is proportional to the current. This is an example of the solenoid, one example of what we could use as an inductor, right? So we know that in an inductor, the magnetic field is directly proportional to the current. We know that. And to the inductance in the device. Again, going back to the solenoid, L over L is mu naught N squared A. And so we know that that there's going to be a relationship with inductance as well. Actually, what was the formula again? It's that's right. Mu naught N squared A. And so we know that that's the inductance for the solenoid, and so we know that the magnetic field is going to be proportional to the inductance as well. All right, so again, V is mu naught Ni, and I has, again, we know the solenoid is what? We know that the solenoid is going to, or any inductor is going to be that L is cap N phi over I, all right? And so there is a relationship with, and of course, we know what phi is, right? Phi is BA. And so I could write something like L is cap N BA roughly over I. And so again, the inductance is related to the magnetic field. They're directly proportional to each other. I already showed you that. Again, I'm looking at, this is in general true for an inductance. And of course, for the solenoid, we saw that magnetic field is directly proportional to the current as well. So everything I'm saying up here is right. So in an inductor, the magnetic field is directly proportional to the current and the inductance of the device. That is true. Magnetic field is proportional to the inductance. Magnetic field is proportional to the current. Okay, we see that. That is absolutely true. All right. So in that way, we know then that the we can show, again, I'm not going to show it here, but we can show using integral calculus okay, we show that using integral calculus, the energy stored in an inductor is, we call it E end, I mean 1/2 Li squared. All right. So again, that's energy stored in a magnetic field, energy stored in the inductor. We can compare this with a capacitor. So just for compare with, for the capacitor, E cap was 1/2 CV squared. Again, similar looking form. Basically the energy is proportional to the inductance for the directly proportional to the inductance for the magnetic energy. For the electric energy, it's proportional to the capacitance. All right, and you have this current squared for the magnetic energy, and the voltage squared for the electrical energy. And this is energy stored. Energy stored in the capacitor, energy stored in an inductor. All right. So again, cannot show you the particular calculation involved with this. It requires integral calculus, but you can see that there's a similar look and feel for the energy equations for both an inductor and a capacitor. All right, let's go do a few problems. I'm going to look at OpenStax 23.55. And we're still in chapter 22 in Cutnell Johnson, but again, we're one off with OpenStax. OpenStax is already in chapter 23. All right, 2 coils are placed close together. In a physics lab, to demonstrate Faraday's law of induction. And in fact, if we were meeting face to face, we would actually be doing the very experiments that I first talked about at the very beginning of the chapter 22 lectures, in the very beginning of part 1. I started the entire lecture off with an experiment. We would actually be doing both of those experiments if we were meeting face to face, by the way. All right, so a current of 5.00 amperes in one is switched off in 1.00 milliseconds. one coil. Inducing a 9.00 volt EMF in the other. What is their mutual inductance? Okay, so OpenStack's 23.55. Two coils are placed close together in a physics lab to demonstrate Faraday's law of induction. Okay, so again, just like the picture that that second picture, the rightmost picture I drew in the very beginning of the part 1 lecture of this for chapter 22. A current of 5.00 amperes in 1 is switched off in 1.00 milliseconds. All right, so the current is changing. It's going from 5 amperes to 0 in 1 millisecond. That's what we'll call that in coil 1. Inducing 9.00 volt EMF in the other. We'll call that epsilon 2. What is their mutual inductance? All right, so I'm going to erase for real estate purposes. Okay, so the governing equation, so I'm going to say that the current is driving in coil, the driving current, the changing current is in coil 1, the induced EMF is in coil 2, all right? So I'm going to essentially say that epsilon 2 is negative m delta I1 with respect to t. That is the overall equation that I'm going to use to solve this problem. I really want to solve for m. But that is Faraday's law in this concept of mutual inductance. All right, well, what do I know? Delta I1. That's going to be I1 final minus I1 initial. I1 final is this current, this circuit's being switched off. So the final current is 0. Minus the initial current, well, that's 5 amperes. So delta I1 is going to be negative 5.00 amperes. That's a change of the current. Delta T, 1.00 milliseconds, or 1.00 times 10 negative 3 seconds. That's how long this is going to take. We're told that the other loop, which we call loop 2, has an induced EMF of 9 volts, 9.00 volts. What we don't know is the mutual inductance. So we can quickly solve for the mutual inductance. So I can say, well, that's M is equal to negative epsilon 2 times delta T over delta I1. All right, M, cap M is equal to negative 9.00 volts. Delta T is 1.00 times 10 to the negative 3 seconds. And delta I1 is negative 5.00 amperes. So the mutual inductance of this 2-coil arrangement will be 1.8 times 10 to the negative 3 henries. Or 1.8 millihenry. That is the mutual inductance of this 2-coil arrangement. Okay, let's look at OpenStack's 23.57. Okay, the 4.00 ampere current through a 7.50 millihenry inductor is switched off in 8.33 milliseconds. All right. What is the EMF induced opposing it? All right, so a 4.00 ampere current, okay, we have basically a current with an inductor on it, through a 7.50 millihenry inductor is switched off in 8.33 milliseconds. All right, so the current is suddenly reducing. It's suddenly changing. It's a steady state current. All of a sudden, the current is going to change. It's going to go from its full current, 4.00 amperes, to nothing in just 8.33 milliseconds. That's a change in the magnetic flux through the inductor, which means there's going to be a self-induced EMF through the inductor. All right, so that's what's going on here. So what's happening here is that this is the self-induced EMF equation. Epsilon is negative L delta I with respect to T. Again, this is self-induced EMF. Okay. What do I know? Well, I know the amount of time. I know what the delta I is going to be, right? It's going to be final current minus initial current. So final current, again, it's being switched off. Final current is 0. Minus initial current is 4.00 amperes, or negative 4.00 amperes. What about delta T? Well, I know that too. That's given to me. 8.33 milliseconds, or 8.33 times 10 to the negative 3 seconds. All right. And I know what the rating of the inductor is. The inductor has an inductance of 7.50 times 10 to the negative 3 henries. So I'm now able to calculate the self-induced EMF. I get epsilon is negative. We have L didt, 7, or L delta expected T, 7.50 times 10 to the negative 3 henries, times delta I is negative 4.00 amperes. And then delta T is 8.33 times 10 to the negative 3 seconds. That implies that the self-induced EMF in the inductor is going to be 3.60 volts. All right, there it is. All right, let's do another problem. Open stacks 23.62. That one says A, calculate the self-inductance. Calculate the self-inductance of a 50.0 centimeter long um, 10 centimeter diameter solenoid having 1,000 loops. All right, we get to use the solenoid equation now. B. How much energy is stored in this inductor? We could use some energy calculation now. How much energy is stored in this inductor? When 20.0 amperes of current flows through it. Yeah, that's the question. And then C. C says, how fast can it be turned off? If the induced EMF cannot exceed 3.00 volts. All right, here we go. OpenStax 23.62 says, A, calculate the self-inductance, capital L, of a 50.0 centimeter long, 10.0 centimeter diameter solenoid having 1,000 loops. B, how much energy is stored in this inductor when 20.0 amperes of current flows through it? And C, how fast can it be turned off if the induced EMF cannot exceed 3.00 volts? All right, so we got some good thinking going on in this problem. All right, so let's erase this for real estate. All right, so the first thing I need to do is calculate the self-inductance. All right, so what do I know? Again, I'm talking about a solenoid. All right, so the general equation for the self-inductance of a solenoid, again, we are given that cap L over L is mu naught N squared A. All right, again, that is for a solenoid. Particularly for a solenoid, and if it's a long solenoid, we can move the L on the right-hand side. All right, so we're going to do that. So little l, we're told is 50 centimeters, or again, 0.500 meters, of course, that's the length. Well, we're given a radius, so we have to figure out, so we're given a radius of 0.050 meters. This is the length of the solenoid. This is the radius of the solenoid. Okay. And then we're given that there are capital N, or 1,000 turns in this length. 1,000 turns on the entire solenoid. 1,000 turns. All right. So, all right. So again, mu naught is the permeability of free space. That's the constant of the universe. We're given little L. We have that. I need to determine little n and a in this equation still. All right, well, a is easy. Well, little n is easy, right? Because little n is what? The total number of loops, total number of turns in the solenoid divided by the length of the solenoid. Very easy. So again, that's 1,000 turns. That will occur in 0.50 meters, or it will be 2,000 inverse meters, or 2,000 per meter, if you will. That would be what n is. What about the area? Well, again, that's pi r squared. And circular solenoid, pi times 0.050 meters squared. So the area of the solenoid will be 7.85 times 10 to the negative 3 meters squared. All right, and that is all that I need. And so what I'll actually do is I'll move the capital L up. We're going to assume, again, the length of the solenoid is 50 centimeters. The area, as you can see, is very small. So L is much greater than A. So we can write that cap L with the approximation, not have to worry about not really have to worry about diverging at the ends of the solenoid, diverging the magnetic field at the ends of the solenoid. We can write this as mu naught L N squared A, again, little l. So finally I can write that the inductance for this solenoid will be 4 pi times 10 to the negative 7 Tesla meter per ampere, or I think that's the units. We'll just not worry about the units. I'm gonna run out of space here. Not careful. Let's see. The length is 0.50 meters. That's L. N is 2,000, but don't forget to square it. 2,000 squared, and the area is the 7.85 times 10 to the negative 3 meters squared. All right. If I multiply all this together, I find out that the inductance of this solenoid will be 1.97 times 10 to the negative 2 henries, or 19.7 millihenry. That will be the inductance of this solenoid. Now we're going to use this solenoid as an inductor. So it's good that we now know the inductance of it. That'll be very helpful for calculating magnetic energy, for instance. Now we know, if we take an inductor off the shelf, we now know how to figure out its inductance. Mu naught L N squared A. Again, I could figure it out quite easily, provided that I'm given this value N. It's quite difficult to try to count 1,000 lines, whatever, of wire turns. It's really difficult to calculate capital N. So you hope that the solenoid is manufactured, and the manufacturer tells you what little n is. All right, part B. Now we want to calculate the energy stored in the inductor if the current is 20 amperes. And so, and this is I'm going to reuse this value for L and put that in the parking lot, I guess. All right, so for part A, we know again that L is 1.97 times 10 to the negative 2 henries. All right, now Let's see, what's the wording? Part B says how much energy is stored in the inductor when 20 amperes of current runs through it. All right, that means I'm going to set my I now be 20 amperes. I've now calculated the inductance of the solenoid that I'm now using as an inductor. So what do I know? The energy stored in the inductor, E sub inductor, is given by 1/2 Li squared. So the energy E sub inductor will be 1/2, again, this 1.97 times 10 to the negative 2 henries times 20 amperes squared. E sub inductor, when I work this out, I get 3.94 joules. Again, it's an energy. Okay. The last part is how fast can this current be turned off? You know, basically the current is going through the solenoid if the induced EMF cannot exceed 3 volts. All right. So let's remind ourselves again what the equation is now. So for part C, I have a limitation. So again, my L is going to continue being the same. I already figured L out in part A. That's a constant throughout this. So again, 1.97 times 10 to the negative 2 henries. Now, given that I'm going to turn off this current, there's going to be a change in the inductor. There's going to be a change in magnetic flux. Well, if I have a maximum amount of self-induced EMF that I'm willing to allow in my design, then I better be careful how fast I turn off the inductor or turn off the current. So why is that? Because epsilon is the self-induced EMF. Because there is a magnetic flux changing in the inductor, because the current in the inductor is being turned off, because there's a magnetic flux changing, Lenz's law is going to oppose that with, again, a self-induced EMF. And what is the equation for that? Epsilon is negative L delta I with respect to T. So I want to limit epsilon to be no more than a maximum value. So if that's the case, well, delta I is going to shut off no matter what. It's going to go from 20. I mean, delta I is going to go what? It's going to go from 20 amperes down to 0, right? So it's going to be 0 minus 20 amperes or negative 20 amperes. That's a given. All right. The inductance is a constant. Of the design of the solenoid that I'm using solenoid as an inductor. I calculate the inductance. That's the inductance of that solenoid, no matter what. That is it. That is a characteristic of that solenoid. That doesn't change. I doesn't change. So what I have to limit here is how fast do I shut off this circuit. So this self-induced EMF, I'm trying to limit it at a maximum. Okay, so my epsilon sub max, I'm being told I do not want this in self-induced EMF to go beyond 3.00 volts, period. That's in my design. That means what do I do? Well, if I maximize a fraction, I mean, I can do so by minimizing the denominator. There's nothing I can do with the numerator of this fraction. So it's negative L delta I over delta T min. And what I want to solve for is delta T min. So I'll just basically change partners here. Delta T min is negative L delta I over epsilon max, the maximum self-induced EMF that I'm willing to allow in my design. So delta T min will be negative 1.97 times 10 to the negative 2 henries times negative 20 amperes divided by the maximum self-induced EMF that I'm allowing in my design. That's 3.00 volts. So the minimum time that this circuit needs to be shut down, we work this out as 0.131 seconds. If I shut this circuit down to 0, 20 amperes to 0, any faster than that, then I will incur a self-induced EMF that will be beyond 3.00 volts, which is what I don't want. I can shut it down in a slower manner. That's perfectly fine. But I guess what I really could have put here is I should have said that T-min has got to be greater than or equal to, this number. But that's fine. I mean, the fact of the matter is that is the minimum amount of time duration that I'm allowing this circuit to shut down. Okay, and so that's the minimum time to allow the circuit to shut down. Okay. Last topic of this lecture. Okay, and I did the same kind of thing, with capacitors. Now I've developed the concept of an inductor. We now have our 3 circuit elements. We have the resistor, the capacitor, and the inductor. All right, and so just like I made an RC circuit back in chapter 18, I can make an RL circuit here. I can put now a resistor and an inductor together to make a circuit. So that's what I'll do next. So my last topic of chapter 22 is the RL circuit. I have now developed the concept of an inductor. Now I have an inductor that I can pull off the shelf and make a circuit. So we're going to look at RL circuits. Okay, so let's draw some analogies here. So recall the RC circuit. First of all, let's go back to the capacitor. Let's go and try to draw an analogy to the capacitor. So recall the RC circuit. What did that look like? Well, I have a battery. And as the name implies, I have one resistor and one capacitor. And battery epsilon, resistor R, capacitor C. Okay? And I was trying to figure out an equation to be able to describe this circuit. And so what did I do? Well, I employed the Kirchhoff loop rule. So use the Kirchhoff loop rule How do I do that? Well, let's start from the bottom of this of the battery. And so I'm going to walk the loop. I'm going to go all the way around the loop. And of course, Kirchhoff's loop rule says what? That the sum of all voltages across a given loop is 0. So I'm going to start from this negative part of the battery and come all the way around and end right back where I started. So I'm going to cross the battery. That's a voltage rise. That's epsilon. And then I walk the loop and I encounter the resistor. That's a voltage drop. What's the rule? What's the voltage rule for resistor? Oh, that's right. It's Ohm's law. It's IR, right? So I will drop. Again, what's going to happen here is I'm going to have a current I. Again, this resistor and capacitor are in series. So again, I'll have a current minus IR. Okay, I continue. And I go and I see that I now cross the capacitor. What's the rule for the voltage drop across the capacitor, well, that's negative Q over C. And I keep walking, I turn a corner, and I finally end up back where I started. So all of this is now equal to 0. That's what the Kirchhoff loop rule says. And remember, I is a function of time, and so is Q. And I say, well, okay, well, great. I have an equation, but the problem is I have one equation and two unknowns. I do not know. My unknowns are, well, I is a function of time, and the charge on the capacitor plate is a function of time. Great. One equation, two unknowns. That means I can't do it. What do? Well, I remind myself, oh, you know what? I know the definition. I know that current is the time rate of change of the charge. And oh, by the way, let's do it in an instantaneous manner using differential calculus. Let's say that the current is the limit as delta T approaches 0 of delta Q over delta T, which of course is the first time derivative of the charge. So instead of having I, what I can do is I can just substitute a dq dt up there instead. All right, and again, this is just review, but I have epsilon minus r dq dt minus q over c equals 0. Let's throw the epsilon on the other side, multiply through by -1. What do I get? Well, I get r dq dt plus q over c equals epsilon, and then let's divide through by r, and I find out that, well, dq dt is equal to dq dt plus q over rc equals epsilon over r. And what did I say again? Oh, I have a differential equation. What do? I have a differential equation that essentially says that, well, you know, I have a switch that I throw. I just get I just turn on the current and I start operating this RC circuit. I need to solve this differential equation. So again, remember, we need to solve this differential equation for unknown Q of T. Now, of course, if we figure it out, it's the unique solution. All right, so again, let's kind of write this a little further up, and this is just review. If we can solve this differential equation, then the existence and uniqueness theorem of differential equations subject differential equations states that this solution is unique. You don't need to keep looking. Fantastic. So the question comes down, can I solve this differential equation? And the answer, as we recall, was yes, we can. And so this differential equation has a solution, is given as Q as a function of time, is C epsilon times the quantity 1 minus E to the negative T over tau sub C. Tau sub C was the time constant for the RC circuit, and it's literally just given by R times C. If I multiply R times C together, the resistance in ohms, the capacitor in farads, I get a time constant in seconds. This is the charging equation. Okay, so let me kind of write in a parking lot for comparison purposes what we have here. So again, that's the charging equation. So in general, for the RC circuit, there's a lot of, it's always good, kind of good to compare, because oftentimes you find in physics they end up reusing the same mathematics again. All right, and so, and I found it funny when I took fluid mechanics in engineering school. Well, I took it after I had my entire physics degree, my bachelor's degree. So I'd already taken electromagnetic theory. And I've already seen the curls and divergences of the fields, all the vector calculus that describes electromagnetic theory. And then I get to fluid mechanics and I find out I already know this math. I already know this theory. And I went to, he was my advisor, Dr. Richard Gardner is his name. I went to him and I said, I'm seeing a complete repetition of electromagnetic theory in this class. He says, yes, you're absolutely right. It turns out that the underlying mathematics that you study in electromagnetic theory, which talks about current flow, what's the current here? Well, the current is there, the current's going to be flowing of charge. Well, in fluid mechanics, it's the flowing of water or the flowing of a fluid, right? Turns out the mathematics is darn near the same. And we're going to see that, we're going to see a lot of this as well here. So our differential equation for the RC circuit was the Q dt plus Q over RC equals epsilon over R. And I found out that I have a charging equation. Q as a function of time is C epsilon 1 minus E to negative T over tau sub C. And tau sub C, that's the time constant that's the capacitive time constant. Tau sub C is just RC. And oh, by the way, if I want to discharge, so again, remember, at time 0, what happens? Well, what's the charge in the capacitor at time 0? Well, e to the 0 is 1. Anything to the 0 is 1. So 1 minus 1 is 0. So the initial charge on the capacitor is 0. And if I let the current go a long time, what happens now is this becomes e to the negative infinity, which is basically 0. And then what ends up happening is I asymptotically approach a charge C epsilon. So I'll maximize the charge to the capacitor, give my C epsilon. That's the behavior. But what if I open up the switch? I have this going, on and on and on. Now I decide, okay, I'm going to open the switch now. Well, essentially what I've done is I've made epsilon go away, and my new differential equation is the Q dt plus Q over RC equals 0. And what's the solution to that differential equation? Well, that's the discharging equation. That's Q of T is Q naught, initial charge before I started discharging, e to the negative T over tau sub C. All right, so this one is charging. Let me write this a little further down. Okay, so this equation, remember, is charging. Recall again that tau sub c is RC, and the discharging equation is Q as a function of time, is the initial charge on the capacitor times e to the negative t over tau sub c. This is discharging. All right, again, that's the review. Now we have a different situation. Now we have the RL circuit. What does it look like? Well, one good way of drawing it is I'll draw a battery, and I'll draw a little switch here. I'll call this A, and I'll have a switch that can go either way. And I have a part here B that goes down like so. My switch S, two-way switch. I have now the resistor, and I have the inductor now. The inductor, remember, looks like a coil. Now I have a resistor R and an inductor L. If I throw my switch to A, I have now connected with the battery. Okay, so I throw the switch to A. To connect the battery. And let's walk the current. So I walk the current, and I'll basically say, okay, well, I'll have, I'll start, I'll basically start here. The current's going to be like basically this. It's going to be up here to the switch, all the way over here. This B doesn't matter. Okay, so I start at the bottom, and again, I'm going to have epsilon. Okay, I continue. Again, I've thrown a switch to A. All right, so again, I've thrown my switch to A. All right, I'll continue with the resistor. Again, there's going to be a current developed in here. All right, and so I'll continue along. And again, the rule for voltage drop for a current across resistor is what? It's minus IR. Continue, turn the corner. What's the voltage drop across the inductor? That's the self-induced EMF. That'll be negative L delta I with respect to T. Continue. Turn the corner, go all the way back, and I end up where I started at the bottom of the battery. That's going to give me 0. And again, I want to consider delta to be so small as to be differential. I'm going to write a differential equation again. So again, I'm going to essentially substitute these deltas for D's. All right. So it's going to be negative L di dt. I'm going to use the first derivative of the current with respect to time. All right. So again, I have a differential equation. But interestingly enough, if I fix it up a little bit, what does it look like? Well, I'm going to have L di dt plus IR, or RI, we'll say. I is the function that I don't know. Is epsilon. I mean, again, I threw epsilon on the other side. Everybody was negative. I multiply through by negative 1, and then that's what I have now. And I'll do one more thing. I'll just divide through by L. All right. So again, I'm going to divide through by L, and I'm going to have an equation that looks real similar. isomorphic, in fact. di dt plus a constant times I, R over L in this case, times I, F equals epsilon over L. The function that I don't know, the unknown function, is I as a function of t for the RL circuit. Look at the RC circuit. Time rate of change of the charge is a function of time. The charge as a function of time is what I don't know in the RC circuit. Plus Q times a constant is epsilon over R. So again, very, very similar. In fact, this is an isomorphic differential equation. This, besides whatever the constants happen to be, this is an isomorphic differential equation. Instead of solving for Q of t, I'm solving for I of t, but who really cares? I could be solving for F of t. I could be solving for whatever function. The physics says, well, the RC circuit means you're solving for the charge as a function of time, charge on a capacitor, whereas you're solving for the, in the LR circuit, you're solving for I in the actual circuit. And of course, I that goes through the inductor. Okay, so what would the answer to this differential equation be? Well, again, it's going to be very similar looking. So let's let me erase my, and of course, if I wanted to discharge, by the way, if I wanted to discharge this system, all I would do is, we're going to talk about, discharge. I'm going to talk about turning the system off. All I would do is throw the switch over to B. What have I done at that point? Well, I've made an open circuit on the left-hand side. This, for the most part, doesn't exist. I've cut out epsilon. So again, the right-hand side of that becomes 0, and again, this is kind of like discharging the capacitor. This is turning off the circuit. All right, and so what will the answers to this be? So again, let me kind of write side by side what my RL circuit material looks like. So again, I'll see something looks similar. I'll write it next to the capacitor. So di dt plus R over cap L. L again is the inductance of the inductor, times I equals epsilon over L. And that is my differential equation. That is me turning on, throwing the switch. Again, we'll say the RL circuit's been dead. It's not doing anything. I'm going to throw that switch and turn it on after it's been sitting for a while. So again, the current just gets started. All right. Now, by the same token, I expect the solution to this differential equation to look very similar. And in fact, it's going to look like this. I, as a function of time, for the RL circuit, is going to look like epsilon over R times 1 minus e to the negative t over tau sub L. Tau sub L is the inductive time constant. This is the rise of the current. The inductive time constant, as we will see, looks like L over R. It has units of time. Okay, that's the rise of the current. Now let's look at this. When time is 0, what do you see? When time is equal to 0, I have e to the 0. Anything to the 0 is 1. 1 minus 1, again, is 0. The initial current in this circuit, as soon as I turn it on, is 0. As time goes to infinity, I have e to the negative infinity. Well, that second term is basically 0. That means finally I would get the answer as if the inductor didn't exist and I just had a resistor, epsilon over R. Basically, as time goes long enough, the inductor becomes basically a piece of wire. It doesn't really factor into the whole circuit, and effectively I just end up getting Ohm's law. But what the inductor does, what the RL circuit does, is that instead of an Ohm's law, when I just have a resistive circuit, just a resistor, I very quickly I have IFT equals IS equals epsilon over R. It goes from 0 to epsilon over R very, very quickly. Whereas here it takes an amount of time to build up to epsilon over R. It doesn't happen automatically. It takes time to build up. Essentially, the inductor being thrown in there slows the current build up down. The current does not get to its maximum value rapidly. It takes time. And I can actually control that time by controlling what L over R is. L over R is a time constant. How many, again, it takes about 3 time constants to get you to practically a full current. Well, if I make the time constant say something big, like, 5 minutes or something, well, that means that I can make this thing so slow, it can take 15 minutes to get a full current. I mean, I have control over that because I can control what inductor and what resistor I stick into the circuit. So I can make the circuit real slow. I can make it so slow that even someone like myself can sit there and with a stopwatch and analyze this circuit or watch it experimentally and take data. I can't take data if I'm trying to analyze a circuit that's going like this very, very quickly. I can't do that. But if I slow it down really slowly, then I can actually analyze this RL circuit. And we do that in the lab as well, if we were meeting face to face. A lot of stuff, a lot of interesting stuff that you're missing. Okay, so, and of course, there's a situation where if I throw the switch to location B and I cut out the battery, essentially it's as if I took the battery out and I made the right-hand side of this differential equation 0. Well, then I have a brand new differential equation. Well, you would expect it, given it's isomorphic, you'd expect it to look a lot like this, and indeed it does. My falling current would be I of t is going to be some initial current, I naught, or we'll say epsilon over R, possibly, e to the negative t over tau sub L, or I naught e to the negative t over tau sub L. Again, this is the inductive time constant. Inductive time constant is L over R in units of seconds. The capacitive time constant is RC, again, units of seconds. And this is the falling current. Okay, all I have left is a couple of quick problems, and then we'll call it a done deal. All right, so let me do a couple of problems out of open stacks. And again, this is RL circuits. I want to do open stacks 23.69. That says if you want a characteristic RL time constant, so if you want a characteristic RL time constant, and design an RL circuit here of 1.00 seconds. And you have a 500 ohm resistor. What value of self-inductance is needed? Okay, so it's not too bad of a problem here. All I really know, I mean, I know the time constant for inductive time constant. It is what? It is L over R. And we want to know, we're basically being told, well, I know the tau bell that I'm shooting for. Here's 1 second. And I know the resistance is 500 ohms. What's the L? Well, solving for L, very basic algebra here. L is, it's going to be basically R tau sub L, or 500 ohms times 1.00 seconds. And surprise, surprise, L is going to equal 500 henries. One of the easier problems we've done in this class. But hey, this is a very important calculation if you are trying to design the time nature, the time varying nature of your LR circuit. This is a problem you have to solve, as simple as it may look. Okay, one more problem and then we call it a done deal. I want to do OpenStax 23.74. A. What is the characteristic time constant? Of a 25.0 millihenry inductor? It has a resistance of 4.00 ohms. B. If it is connected to a 12.0 volt battery, what is the current after 12.5 milliseconds? All right, again, 23% for A. What is the characteristic time constant of a 25.0 millihenry inductor that has a resistance of 4.00 ohms? Again, L is 25 millihenries and R is 4.00 ohms in my RL circuit. And then B, if it is connected to a 12 volt battery, that's my epsilon. What is the current after 12.5 milliseconds? Here's your T. All right. So for real estate purposes, let's erase. All right. A. So what do we know? As I pointed out in the problem, we know the inductance, the self-inductance, is 25.0 times 10 to the negative 3 henries. We also know the resistance, and that is 4.00 ohms. All right, and so the time constant, this is what we're after for part A, time constant tau sub L is simply L over R. All right, so again, just like the last problem, 25.0 times 10 to the negative 3 henries divided by 4.00 ohms. We find out that the time constant is very fast. It's a very small time constant, so 6.25 times 10 to the negative 3 seconds, which is 6.25 milliseconds. This LR circuit's very, very rapid. I mean, 3 time constants, roughly, you get about 97% of your full current. Well, 3 time constants is 3 times 6.25 milliseconds. I mean, that goes by like that, right? So this is a very fast RL circuit. All right, so for part A, let's put this in a parking lot. Tau sub L is 6.25 times 10 to the negative 3 seconds. I mean, again, this is what I put down for the answer for part A. This is what I'm going to put in the parking lot because that's going to be more useful in my calculation. All right, so this is part A. Now I'm going to do part B. I'm going to use part A actually to do part B. So part B. Now I go to my current rise equation. All right, so go to current rise equation. I of t. Again, I of t is epsilon over r. That's why 1 minus e to the negative t over tau sub L. That's what I want. All right. And what I'm looking for essentially is I'm going to say, well, I want I of T1. All right. That's going to be epsilon over R times 1 minus e to the negative T1 over tau sub L, where T1 is 12.5 milliseconds, or 12.5, and this is stated in the problem, times 10 to the negative 3 seconds. And it's literally just a matter of plugging the equation in out of the box, right? So I of T1, so I of T1, the T that I'm considering here, epsilon, what is epsilon? We're told that's 12 volts. That's the voltage source, divided by the resistance of 4.00 ohms. And then that's 1 minus e to the what? Negative T1, negative 12.5 times 10 to the negative 3 seconds over, trying to itty bitty here, 6.25 times 10 to the negative 3 seconds. Again, any transcendental function, the argument's always got to be unitless. So second over seconds is unitless, right? When I calculate all of this, I will find out that I at T1 will be 2.59 amperes. Now, at this point, it's gone about 2 time constants, roughly, almost 2 time. 2 time constants will be about 12.5. It is 2 time constants, actually, 12.5. So again, you're talking about what is it, 68%? Or is it? I don't remember. Anyway, it's two time constants as well. It's we can calculate it right now. If I have my calculator, 1 minus e to the negative 2, right? So the maximum is the maximum would be 3 amperes, right? 12 over 4. So 1 minus e to the negative 2. So two time constants is 86%. So that means that in two time constants, your current is at 86% of its maximum, right? And so at that point, you're pretty well along your way. The maximum current is clearly going to be 12 over 4. If I didn't have the inductor there and I just turn this current on, it would go right to 3 amperes immediately, or very, very, very quickly. Whereas the inductor slows it down, so at least it takes 3-ish, or a little more time constants to actually get to a more or less a fully developed maximum current. All right, so that is all I have for chapter 22.